Hey, Aliya, thank you for coming in. Really just magnificent and wonderful the work you're doing across so many different dimensions, making global contributions. In fact, you're speaking and judging global innovation at GTEx, which is like the world's largest tech conference. I think the estimation is something like 200,000 participants. So it just speaks to your capabilities and your success history. So thank you for coming in and sharing your insights with our audience.
Yeah, thank you very much, Stephen. It's a great pleasure to be here today, and thank you for this amazing interview.
So, Leah, I mean, we had a long interview before, about an hour, and so I recommend the audience go to the prior interview, and they can find that under IEEE TEMS or ACM and other channels, where we got into your history and then kind of the inflection points in your life that made this wonderful career that you have. But that was maybe a couple of years ago now, right? A few years ago. So let's do an update. Since that last interview, tell me about some of the things you're working on.
Yeah, sure. So for the last couple of years, I've been focused with my team on three main topics, and the reason it's important to make a small note before covering these three topics that I believe that all these three topics have a huge future potential for both of our world and for sustainability and for AI for good general topics. So the three main angles we've been focused with my team for the last couple of years is first of all of building and launching our platform for engineering teams and specifically for manufacturing, using AI as a co-pilot for an engineer and as a tool which will help to make all the manufacturing processes, specifically in metallurgy and machinery, much more efficient, quicker, and advanced. So this is one tool, and it's a software platform, which is basically a co-pilot for engineers. And we launched it successfully with two metallurgy companies, one in MENA region and another one in India. And currently we are growing our solution for other companies. Second, we've been focused on working on our research in artificial consciousness because probably I covered it briefly during our previous interview with you, Steven. I do believe that we do need a novel architectures for AI. And it's not about like artificial intelligence, but rather about consciousness itself, because human consciousness, it's much more broader topic than just an intelligence. And I believe that when we will launch a proper architecture which will reflect kind of idea of human consciousness, it will provide a much more, I would say, smoother and efficient approach to calculations because consciousness it's all about creativity and we don't need only a way to generate information as AI is doing right now, but rather to create things and it will provide a solution to solve much more complex problems. And the third angle, we've been working for last 2 years and we launched a lab in quantum software and quantum computing. So we have our own lab for quantum computing algorithms and currently building our lab for quantum hardware for different solutions in quantum chips and for mechanical, I would say, approach to how to provide a way to bring information from a classical, I would say, format to quantum format. And fourth direction, it's a bit new one, but we are currently working on our own foundry in the many regions. So we're gonna build our own foundry because we will need it for our own, I would say, calculation and in order also to serve the market. So this is a bit of overview of our recent updates for the last 2 years.
So that's really interesting. So let's dive into this a little bit deeper. So you're creating quantum algorithms. So these are algorithms that can simulate quantum capabilities, right? And you can use this to solve various problems. These quantum algorithms are ones that can work on a typical classical computer, right? And making the classical computer perform like a quantum computer. Is that correct? Well, and
Yeah, yeah, that's correct. For software side, you can use like existing computers, and you can just how to say use another level of calculations and computation, because you probably it's basic of quantum computing. They can calculate various things simultaneously. So comparing to the classical way of computation, which you need like step by step, and it can take you like, I don't know, many years, for example, to calculate possible decisions. For example, if we talk about, I don't know, solutions for advanced alloys, for example, for advanced aluminum alloys. A classical computer will need like, I don't know, 10 years to calculate new solutions of alloys. And with the quantum computing, we can calculate within, I would say, 2 days, a new types of alloys, which will be much more efficient and which can be used, for example, to reduce costs and timing to supply these alloys in aerospace, for example, for new types of aircrafts. And it can solve billions and billions of dollars for companies like Boeing, Airbus, and for smaller suppliers.
So your quantum algorithms then, you're doing more than simulating quantum on classical computers. You're also using your quantum algorithms on quantum hardware. Yeah.
Yes, yes, exactly. And that's why we are also building our own quantum hardware, because we do believe that it's important, because when you can match together both your own hardware and I would say your own software, it provides much more like better and efficient way. So, for example, one of the things we are working right now is a multiplexer. It's a cryogenics multiplexer that normally works at low temperatures, and it provides an alternative. So how it will be able to provide an input from, I would say, classic channels to and convert them further on to quantum channels and quantum states. And it provides a new level, I would say, of quantum hardware overall, and a way to work further on with quantum chips and quantum hardware.
So you're building your own quantum hardware where you
Yeah.
have quantum algorithms. Because you haven't completed building your quantum hardware yet, have you, or are you still building it? So on your quantum algorithms, when you're running it on existing quantum hardware, using like IBM or Quantinuum or other companies right now?
Yes, yes, exactly. We are using currently IBM. I believe they have great architectures. Continuum is also they're doing great, and we are using there also computational power. But the main goal is to build our own hardware, because it will provide a much more efficient approach to solving, like in our opinion, complex tasks, and I would say a specific match between our own architectures and design, for example, of our own chips.
Right. So when you're talking about building your own foundry, that's a chip foundry, but it's a chip foundry for quantum chips.
Yes, yes, exactly. Yeah.
So that's expensive. So how do you manage that kind of financing for something?
So far we've been doing it on our own funds, because I still have the part of my family business and family activities. So I have this, I would say, a chance to fund it on my own. But of course, we do plan to fundraise external resources probably early next year for Foundry itself, because of course it has lots of costs, because currently like we have enough revenue from our clients to cover these costs for research, for development, and I would say to start for a Foundry. But of course, for a larger project, we'll need like external resources. And basically, like for previously, we also had a couple of grants. So we also fund some of our activities and research through grant programs.
So what you're doing is you got quantum algorithms. You can use quantum algorithms on classical computers, right? Where you do quantum simulation. You're using your quantum algorithms on existing hardware like IBM or Quantinuum and others, though you like the IBM architecture. But you find that to optimize what you're doing, you want to build your own quantum hardware, and that's why you're creating a foundry so you can create your own quantum chips um, for your quantum computing. Okay, so you also indicated that you're in manufacturing. Is that manufacturing um, in optimizing materials, new kinds of materials, novel materials? Is that using your quantum system or AI machine learning?
So far for manufacturing, we use a classical AI machine learning, but with our new architecture, which provides, I would say, a much more efficient way to analyze complex things. For example, we can do much more, I would say, through our existing AI architecture, we can do much more efficient, for example, simulations of molecular systems for new materials, and also apply this to manufacturing processing, because we can do also digital twins for manufacturing processes, and through this provide an optimization for our existing clients. And further on, we plan to test our quantum software later this year to do again like more accurate and more efficient approach to simulation of molecular systems. And specifically, since it's a quite complex molecular systems, when you're speaking about, for example, aluminum scandium alloy, which is broadly used in aerospace. And we use also classic techniques like circuit knitting to break up different larger molecular systems into smaller simulation problems. And we also use like quantum embedding, for example, for our clients. And overall, like, I don't want to overwhelm you with lots of technical things, but it provides like a more, I would say, smart approach to analyze activity during chemical reactions, and provides this, I would say, and actually provide these solutions through overall systems. And we currently collaborate, for example, with one of our manufacturing clients and metal clients in order to create also a small hub for new types of alloys, where we can use and develop automated methods for different active space selection, which is suited, which will be suited to study not only corrosion, but different types of and manners of chemical reactions that take place on different surfaces. And it can be then widely used both in aerospace, in automobile, in shipbuilding, and it all can be done through like I would say merge between our quantum software architecture and existing our I would say long-term experience, I would say, with manufacturing of alloys, because probably you remember previously I had a background in we produced our own alloys, so that's why I know quite good the area of and how challenging it is in aerospace specifically to test and to implement new types of alloys.
So that's fascinating. So we covered your manufacturing process where you're using AI machine learning on using classical computers, but also potentially then you can use quantum computing, right? For new kind of material science, molecular simulations, things like that. Um, so and so you covered a series. What were some of the other areas you covered that was new?
So it's not new, it's elaborated, because probably you remember about my Kosmos City project. So we are currently we bought the land in Abu Dhabi in UAE, and we are implementing it. So we had the land in US, and we thought to build it there. But based on our current angle, I mean, of all the activities we are developing and growing, we decided to focus and to build the project in UAE, the Kosmos City, which I will briefly remind. So the project is about creating an innovation hub for space tech and future tech focused startups. The core in this specific project will be our own production facility with the foundry I mentioned about for quantum processes, for chips manufacturing, and for new types of alloys for aerospace. It will be, I would say, the part of this industrial cluster. And then it will be also R&D facilities and educational facilities for engineering. And what is important also, I would say, the whole, I would say, ecosystem and infrastructure. So the people can live there, can work there, and can create together. Because I do believe that the future and the next step in breakthrough, both in AI and quantum processes, is when bright minds from different areas like chemistry, physics, mathematics, psychology, even because psychology can bring a huge angle and new developments for AI and quantum processes. They they are brought together in one physical place, and where they can work and co-create together various projects for our future, for our worlds, and for space. And yeah, so that's also a new angle of what I'm working on right now. But it's all, as you probably noticed, it's all interconnected between each other.
Right. So what you're saying is you originally were purchased a bit of land in the U.S. with the idea of building kind of like an innovation tech hub or a city almost like a, and then you decided to put it in Abu Dhabi, right?
Yes, yes.
And that'll be at the location of your foundry and all of the other components. So it's basically all the things you mentioned are interconnected with this kind of innovation hub city focused in this area. So that's really interesting. Okay, so let's kind of delve into each one of these areas in the future. So, are you doing anything in biomedical innovation right now?
We have a small research project. It's regarding longevity because I'm I'm a huge fan on my own about to live longer, healthier, and happier because I need the solution for myself. And I believe that through, again, like both architectures of artificial consciousness and both with algorithms using quantum software and quantum hardware, we can bring new, I would say, ideas and new formats of how we can work with longevity questions. And one of the research we are doing right now, it's about creating, I would say, a foundational model, which is basically like a human atlas, which is covered, I would say, different processes and I would say analysis based on both like human genetics, biochemical processes, biochemistry, and it provides also, I would say, we call it a human body functional model. And the idea of this research is how we can combine together the analysis of different, I would say, processes, specifically also putting a huge attention of person's environment, his emotional state, and his physiological states and psychological, because we're not bringing the angle only to genetics or, for example, or only to biochemical reactions in the body, but also what is important, it's, I would say, epigenetics processes, which are reflected always through our environment and through our emotional and psychological processes, and how we can capture all them together and create through this, I would say, this, I would say, personal, I would say, flow of how the person is aging and how we can change these processes through different molecules. So, for example, how we can use like personalized. So basically, this solution can bring how we can create personalized drugs or personalized approaches to prevent aging and to make person live longer and healthier. And it will be kind of like his personal plan. So not the plan which you use like for everyone, but very, I would say, personalized medicine. And it can be used, so our model can be used in, like, I would say, rejuvenation of drug research. And for example, it can provide like new angles for drug testing to laboratory testing, and can bring rejuvenation therapies to humans more quickly. Second angle, it's like also development of new treatment methods, and like using specifically these physiological needs. And of course, like it can also be also interesting to see these interconnections between all major biochemical and physiological reactions. So this is the research we are working on right now. But it's kind of like, so right now it's more, I would say, deep tech angle. We plan to do the product for this research in next couple of years.
So that's kind of fascinating. So you're working on longevity. You're definitely in biomedical innovation, but you're really interested in the epigenetic kind of disturbances that occur with aging, right? And so that sounds like some of the work that Yamanaka did, and then of course David Sinclair at Harvard, um, some of the work at Altos Labs. So you're excuse me, you have an interest in biomedical innovations. That's fascinating. And you have this investment in quantum computing, and NIST, this maybe a couple of weeks ago, came out with the 3 quantum set algorithms, right? Officially released them.
Yep.
And do you feel then that quantum computing will go to the mainstream in 10 years or 5 years or 3 years?
Well, my personal approach to this, I believe that the more companies, scientists, and labs are working around the world for novel architectures for chips, building quantum computers, and so on, the faster we will accelerate the progress in this area. So I believe that quantum computing will grow rapidly in the next 3 to 5 years, and we will be able soon to create a larger qubit system and larger computer with larger qubits, and it will provide an acceleration in quantum development overall. And I think that it's really important. That's why, for example, we are personally focused on multiplexer and on quantum chips architectures, because all this can be a next, I would say, step to building a large quantum computer, which will be, I would say, much more efficient than existing solution. But yes, definitely, it will be a growing area for the next 3 years.
So right now, quantum computers are having problems solving, uh, you know, practical problems, right? And so
Yeah.
there's limited application right now. And there's this idea of a universal quantum computer that could be applied to a much broader array of problems. But we'll never get rid of classical computers. The quantum computers can't do everything. They can only do certain kinds of things, right? Well, and do you think that broader application where it's now solving on a regular basis with most companies, molecular interaction, novel chemical materials, it's involved in design of new kind of batteries and things like that. Do you think that will be in 3 years, or do you think it's going to be more like 10 years?
Well, I believe it can be 3 to 5 years, because what I see around the world now, it's different. I would say how quantum computing is also used to optimize the quantum computers itself. So basically, how we use our own calculations to optimize the processes inside quantum computers, both like with chips, with batteries, with all the components we need for quantum computing. So, and I do believe that the next step will be, I would say, the application of all these to probably even merge together both classical computers and quantum computers. So we could, I would say, create an efficient way of using both of them in different types of operations, and find a smarter approach where and which kind of algorithms should be used.
So, we looked at biomedical innovation, where it's going, and you're really interested in this kind of epigenetic damage that occurs with aging. And if you can erase that damage, then maybe you can do some rejuvenation or age reversal or some of the things associated with aging. So that's really interesting. You're actually invested in quantum computing, and you think that more practical application to be more widespread, let's say 3 to 5 years. So that's interesting. The underlying chip technologies, not just in quantum, but in general, uh, what are your views on that? Do you think the computational power is going to continue to increase, uh, but become more energy efficient? For example, have you looked at what's happening in that space? Do you have any thoughts, I guess, about the semiconductor industry in general?
Yes, but I will just explore a little bit about increase of computational power because that's one of the goals, I would say, of my personal goals is to reduce amount of computational power with novel algorithms, and that's why we're digging deep into consciousness itself, in the topic of consciousness. Because, and I'll explain why. Because how our brain works, we don't generate tons of information. For example, like how a little baby, how they learn. They don't need millions of pictures of cats to understand that it is a cat. It starts to understand it through another processes of learning the information. And for example, in order for us to make the decision about, I don't know, where we'll go to travel for our holidays, we don't need to analyze millions of data and then calculate the decision. We make these decisions emotionally sometimes. And this one of the small clues. I'm just giving you some thoughts and some ideas, like what we are currently working on, that it can provide a decrease in computational power because one of the, I would say, architecture based on artificial consciousness we are building. It can provide a way how we can create and through these algorithms, how we can create solutions as a creativity act, as a human being does, rather than generating lots of information, and it will help to decrease the computational power. Another way is, of course, another angle is, of course, the semiconductor industry. Well, I believe, of course, this industry. It's growing now, and it will grow much more. And I believe that the next, I would say, breakthrough will be both in superconducting qubits and in semiconducting qubits. So I'm a strong believer in these two areas. There is, I would say, different angles of how, I would say, different teams approach to working to chips. But for me, the next breakthrough, it's superconducting and semiconducting chips, and they are the most, I would say, interesting ones.
Yeah, and I guess there's photonic chips as well, right? So once they use light.
Yeah. Yes, photonics is good, and we used to give an experiment on photonics one. Well, both of them, like superconductors and semiconductors, and even photonic, they have their pros and cons. And in my opinion, the photonic one, they can be much more, I would say, scalable solution compared to superconductors and semiconductors. But I would say for photonics, sometimes, in our opinion, but it's again like it's one of the approaches we were studying. That photonic components, it's kind of like can be challenging, specifically with light structures. But so compared to superconductors, it can be sometimes quite challenging to navigate this light structure. It can be, I would say, sometimes less efficient.
So that's really fascinating. And what's your feeling about existing AI machine learning? So you're creating your own novel algorithms that you believe are more efficient than the ones that are out there, because you're trying to model what's happening in the human brain. And as you indicated, a child can be shown a picture of a cat, doesn't need, a million pictures of a cat to be trained. And so you're working on some kind of new algorithm, which is more efficient than the ones that are out there that are like categorical deep learning or things like the transformers or diffusion models for graphics and things. And so can you describe that algorithm in more detail? Like, how does it work? And
You mean for artificial consciousness, right?
right,
Yeah. So basically, what we brought together, it's uh, four main areas, which are, in our opinion, human consciousness is based. So the first one, it's I mean, of course, like we took all the classical processes of human brain, which are broadly studied already and broadly described, and classical neuron systems. But what we brought as a new angles for this architecture. So the first one is human emotions. So how neurotransmitters in our brain, how they organize these emotions, and how these emotions they can influence to our decisions, because this emotional approach to bringing the decision brings we are not very rational actually people. We make all the majority of our decisions based on emotions rather than pure rational calculation and approach. And this saves us, saves our brain a huge computational power. So this is one angle. Second angle, what we brought also to the architecture is psychology. So this is basically how psychological aspects of our brain is made. So, for example, what is fear, what is anxiety, what is happiness, and how this is connected with our emotions, with our neurotransmitters, and with making the decisions. And we brought also together, we made our own research of psychological patterns. So we had a focus group with Middlesex University, and we used BCI technologies, so brain-computer interface, to analyze different aspects of what's going on in human brain when there are different, like, for example, situations in life where human can feel anxiety or can be under pressure. So how he's making decisions and what's going on in his brain. And we also put this type of, I would say, architectural processes that we designed based on this to the model. Then the third angle is what we also brought is the learning processes. So how the human brain, how we learn. So how we learn when we are small, how we learn when we are grown ups, and what, for example, how the human brain acts, and what are the learning processes, for example, when you learn a new language. And the fourth process that we described and put it inside the architecture is the creativity. So our creativity is based on different, I would say, angles again. And sometimes it's reflections from the environment. Sometimes it's the past information that we took and we combine it in a, I would say, in an interesting way. And we, I would say, played with all these types of what is creativity about, and we try to investigate how it works through human brain, and again put it to the architecture of artificial consciousness. And we are currently also working on, I would say, the theory of quantum brain and quantum consciousness itself, which was widely described by Sir Roger Penrose. So what is quantum brain and quantum state of human brain and quantum consciousness itself. And we are playing around this theory bit and experimenting in virtual environments, making simulations. So how it can be visualized, so how this architecture can be presented. And also we are working also on EM field, electromagnetic field theory, and how this EM field theory can influence our brain and our consciousness. So basically, how our brain can operate with different types of information and signals which comes from the environment. So we are playing around these types of, I would say, data and how it can be structured to create an artificial consciousness.
So that's really interesting that you're trying to marry all of these different aspects of human behavior, emotions, psychology, kind of how we're structured, even this quantum consciousness idea. But to bring it together into kind of a unified system would be very difficult, right? Because they're like different things. Like the neurotransmitters are different than this idea of quantum effects in the brain. Um, I could see that as being a very difficult problem to model. And so,
Yes and no, because somehow it's modeled with you, with me, with our body, with our brain. So it means that it can exist. So it's not impossible. It's possible
yeah,
because we are, as a human beings, we represent that it is possible, and we are just putting it in different pieces, trying to investigate different pieces on its own, and then to combine it all together. But basically, like all the learning theories help here a lot because, again, like imagine a small baby. They don't have all the, I would say, they can't do, I don't know, three languages in the age of two. They're learning
right.
like step by step. So same way we are bringing this learning process to building our complex architecture.
Again, it's all very fascinating. What do you think AI, machine learning, the transformer models, the diffusion models, where are they going? There's rumors of this new model from OpenAI, codenamed Strawberry or Q Sharp. And in fact, NIST, there's a news article I saw today that NIST is already working on them. So the National Institute for Standards and Technology, which is this US government kind of entity, is now looking at all of the existing, or there's a requirement, right? Any of the new models before they release this has to take a look at it and to test it. So it's like a requirement. So this next edition is from OpenAI has already been tested. Anthropics, all of them are being tested. Uh, this new one is supposed to be much more capable. And uh, do you believe then that kind of the scaling laws with these large language models are going to continue so that the more compute you apply to it, the more uh, optimized data that you apply to it, the better they're going to come, and that continues to scale with new capabilities, emerging capabilities. Do you think LLMs will create an AGI, or do you think it's not? That's a dead end.
In my opinion, it's dead end because LLMs, what I previously explained, they just generate information. They don't create it, and it will need so. And it's dead end both from technological perspective, from sustainability perspective, because they will need more computational power, more resources. It means like more of CO2 emission and lots of data storages and so on. It will be continue to be much more expensive. And well, in my opinion, the AGI, it's and by the way, we've been recently discussing with Ben Gersel, who is a father of AGI AGI, and well, we discussed that we need another approach to AGI. It's not about like only language, because again, like imagine yourself only with a language. You're not just a language. You only syntaxes or only, I would say, these parts of your brain and of your intelligence. You're much more broader system as a human being. You have other sensory inputs, you have other processes, you have emotions, and so on. So LLMs, it's a dead end, and I believe it's just, well, in my opinion, it's a business and investment race now because it's all about like how to make a larger valuation for the company. How and so far, of course, like OpenAI, they're doing great because they created the most scalable solution so far, which is broadly used between different companies and individuals. But it will be, in my opinion, the next race for a couple of years. But then a new solution will come, for example, like artificial consciousness or other AGI architectures, and which will bring more efficiency to the industry. But so far, well, in my opinion, just a classical venture capital race right now.
Well, that's fascinating. I mean, you're embedded in all of this, so it's not like you're doing this as an outsider. You're embedded, researching this all, and so if you were to look or 5 years out, what would the world look like if you could make a prediction? What will it seem like as an individual?
Well, as an individual, and you probably remember my fascination with space exploration. My big dream and idea that in 5 years we will have a uh, artificial consciousness or AGI, we can call it in that way, that will cooperate with us in order to help us to develop more advanced materials, spaceships, space constructions, 3D printing for space, and accelerate space traveling and I would say space exploration. And it will help. So through this novel system, it will help human beings not to replace humans, but to make humans more efficient and to help humans to organize all these routine tasks and to dedicate themselves to more creative tasks and to more strategical things. And the second angle that I believe that next 5 years we will see a growing way of different communities of people who are interested to work together and to create together because the world changing rapidly right now, and the next level of organizations, it's not a classical, I would say, vertical organization where everything belongs to one person, but it will be a diversified, I would say, even like a format of, I would say, community format organization and structures where there are multiple individuals who create together and who can bring in democratic way their solutions and create together, and not rather, I would say, about having a power within one hand of just one person who is founder and CEO. So it will be a next 5 years prediction, and of course, like we'll see that huge growth of quantum computing, quantum software, which will be used broadly in discovering new types of drugs, of making our life better and bringing sustainable solutions to our planet.
Well, that's really, really fascinating. So now you've given a prediction of where you see the world in the next, let's say, 5 years, and you talked about all the leading areas that you're invested in, and you actually have teams working in. And you're going to be at GTEx Dubai in October, so I'll see you there. We'll be judging and speaking as well. Do you have any final sort of questions you want to leave the audience or recommendations? And that's the last question.
Yes, sure. So I would leave a question, and both recommendation is to always grow and develop yourself as a human being in multiple angles, in both emotional, physical, psychological ways, and to always focus on your imagination and creativity, because that's, I would say, the most crucial part of how to make your life interesting and how to make life on our planet better. So this is my recommendation, and my question to the audience will be: so, how you can using your imagination applied right now to solve unsolvable things.
Well, thank you, Aliya, for coming in and sharing your insights and great recommendations as well. I mean, we covered a lot of different topic areas from, new chip technologies to quantum inspired computing to actual quantum algorithms. and the underlying hardware for quantum to AI machine learning, and how that can be used in novel ways to consciousness and what makes a human brain work the way it does. And you're trying to figure all of that out. And then you also explore the future of the world. And you're already doing applications like in novel materials and manufacturing. So again, thank you for coming in and sharing your insights with our audience.
Thank you very much, Steven. It was a pleasure to be here today.
Thank you for listening to the Brand Called You videocast and podcast, a platform that brings you knowledge, experience, and wisdom of hundreds of successful individuals from around the world. Do visit our website www.tbcy.in to watch and listen to the stories of many more individuals. You can also follow us on YouTube, Facebook, Instagram, and Twitter. Just search for the Brand Called You.